So let's go back and see what we were discussing. So we said that this is assuming that we have a perfectly secure crypto system. And we know that, we said that in encryption system, the only thing that is hidden from the eye of the adversary is only the choice of the key, right? Otherwise, the message, the space, cipher space, everything is known to the adversary. So the adversary already knows with what probability M0 is chosen, with what probability M1 is chosen. And then we define two different algorithms for the adversary to, try to see if the adversary can win this game, provide a good guess. So the first guess was basically to do what we call a random guess. And when the probability, the adversary would do a random guess, no matter if the what ciphertext we show him, with a, maybe he would flip a coin and he would say with the probability of 50%, it is M0, or maybe other 50%, it is 1. And then we went ahead and we said that, okay, since we say that this is unconditionally secure, so adversary would spend some time offline. He would plot this, draw this computational tree, the encryption of all messages with all possible keys. And then he has this tree. So given this tree, then his strategy is, as we said, every time he sees a ciphertext, we would flip a coin, he says M0 or he says M1. And so on and so forth for every ciphertext. And we see that in 4 of these branches, he happened to win if he correctly guessed. Then, after we compute the probability of, the success of this algorithm A, then we end up by 50%. So as we expected, no matter what distribution of message we have and what distribution of key we have, how we choose our key, how we choose our M, then the adversary wouldn't win this game with the more than 50% chance. And then the second strategy that we discussed was a little bit different. We know that, this probability would give us a very good hint for the adversary to choose if to choose the right guess. We are giving him the C0. So then the adversary's goal is to tell us if this message is M0 or the message was M1. And then we let this to be alpha and beta. And then he would actually output M0 if alpha is greater than beta. Whatever probability over here is larger, he's going to tell either is M1 or M0. So now that adversary knows this is the logic of the algorithm of the adversary, then we said that using that computational tree that we have in the previous page, the adversary has, he can go ahead and actually do this computation. So we said that this probability, with the help of Bayes theorem, we can represent it as this second term over here. And then we said that the probability of C equal to C0, we just let it to be, is a constant. And then what we have is that given that M is to compute these two pieces, that would solve our puzzle. So what this says is that what is the probability of getting a ciphertext 0 given that the M is 0? So for that, we can go back to our computational tree. This says that given that the M0 is chosen, what is the probability of having C0? And that is exactly to come down to this branch. And that probability is the probability of key 0 to be chosen, right? So we said that is probability to have key 0, and that probability is nothing but Q. And similarly over here, we said that in order to simplify this term using our computational tree, what is the probability of C to be given M1? M1 is chosen. What is the probability to have Z0? It is 1 minus Q. So we would just replace it using the computational tree. And then we would be able to compute alpha and beta as these terms. So we had another, assumption that we choose the key uniformly random. That is key 0 is chosen with probability of 50%, and key 1 is chosen with, again, probability of 50%. If we replace this q and 1 minus q, which is 1/2, then we would end up to having these two terms over here. And looking into these two terms, you know, the time that now we would be able to compute the correctness of this algorithm A. And this algorithm alpha is become greater than beta when p is greater than 1 minus p, and that happened when, you know, the probability of message M0 is higher than probability of message M1, and otherwise vice versa. So what does that tell is that no matter what value of p is, or 1 minus p over here, so the maximum probability that A can achieve is actually the maximum of these two, which is basically distribution of the message space itself, that everybody knows this one in the first place. We assume in the definition page that the probability distribution of M and C is known to everybody, right? Actually, C doesn't have to, C there's no probability distribution for here, but M does have a probability distribution. Everybody, adversary in the first place knew this probability distribution. So after spending a lot of time and plotting the computational tree, that computational tree did not help him at all. He didn't learn anything but what he knew in the first place. So this concludes us that given unlimited amount of resources to this adversary, as long as our algorithm is perfectly secure, then he should not learn anything but the message distribution itself. So remember, guys, that we said that the adversary would take this time offline to, you know, plot this computational tree. There is nothing more than this that can happen in the system. So we know that in the first place, plotting this computational tree for when message is like n bit, and then the key is also n bit, then this computational tree would become extremely huge, and it would take many years probably for the adversary to even get too close to where this computational tree should look like. And therefore, we assume that even though we give this computational tree to him, that is the maximum thing that he could do, this did not help him to learn anything more than what he knew in the first place. And that's why it is computationally secure. So let's move forward with closer examples that we would get to compute something that we actually know as stream cipher. So if you know, we've been talking closely, talking about Vernon one-time path. So again, with you know, mathematically showing the way that the stream cipher works is that the encryption algorithm would basically choose, you know, a message M, we would be chopped to different messages M1 to Mn, and we have the key string, and also the ciphertext string. A string would be computed as encryption of key I and Mi, and this is how mathematically we would show a stream cipher. So we said that the Vernon one-time path is perfectly secure under unconditionally, you know, powerful attacker. So let's really now compute and see how is it so. Remember, the way that the Vernon worked was that the encryption algorithm was just like XORing MI and the KI. So the XOR operation was the secret sauce of this algorithm. So just like previous example, I think it's exactly the same. Instead, now we are giving actual values. So the message is could be either 0 or 1. And then we said that the key is chosen uniformly and independently from the set. So that means that probably the 50% 0, 50% 1. And then we said it achieves perfect secrecy under choose and only attack, even though adversary has unlimited computing power. And let's see how it is actually computed to be correct. So this is the proof of Vernam one-time path. So we say that for any algorithm A that you can come up with, any algorithm A, in the previous page we came up with 2 different strategies that algorithm A could work out, but now we are generalizing for any possible algorithm A. And this algorithm, we say that the probability of giving a CI to this algorithm A and correctly output that the output is MI is going to be less than maximum of P0 and P1. And where P0 is the probability of having message 0 and P1 is the probability of the message to be 1. And to be a bit more generic before we solve this problem, we assume that no matter what algorithm A is, by giving the ciphertext C0, it would output the corresponding message is 0 if with probability of R, and then with the probability of A, given that ciphertext is C1, and it would output M to be 0 with probability of S. Okay, so now that we know this, let's draw this computational tree again against this attacker and see what we would achieve. The first thing first, let's summarize our algorithm A. No matter what algorithm A is, we said that A given C equals to 0 would output the message to be 0 or the message to be 1. According to the definition in the previous page, it says that the probability of C to be 0 and the message is 0 is R. So with that, we know that this probability is R, and this is going to be 1 minus R, right? So this is the guessed M, and this is the probability. Oops. Okay. And then again, we would have similar thing. Now algorithm A, by given that the ciphertext is 1, again, he would output 0 according to the definition by probability of S, and he would output 1 with probability 1 minus S. So we are just trying to be generic now, right? So this is the definition of our algorithm. It will come up with different probabilities. And like we said, in this example, let me change my pen. Okay. So in one-time path, we have this message M1, M2, and all the way to MI, and all the way to, MR. Suppose that they are being transferred, and then the algorithm is constantly outputting C1, C2, all the way to CI, all the way to CR. So suppose that we are in ith computation. So we are encrypting the message ith. And since we said the adversary has unlimited computational power, he can start to do the plot the computational tree. So we know that MI, with probability of P, we get to 0, and then with probability of P0, we get to 1. And again, by choosing the key to be 0, K equals to 0, and for this case, K equals to 1, we get to 0, because 0 encrypted with 0, the XOR with 0 is 0, 0 XOR with 1, key is 1, we would get 1, right? And this has 0.50% of probability, and this one has also 50% of the probability. How so? Because we said that in one-time path, keys are chosen uniformly random, right? So probability of key to become 0 or probability of key to become 1 is equal. Similarly, we can do the similar computation for over here. So we can have key again chosen to be 0 and key is chosen to be 1, and the probabilities are again 50%. So message is 1 XOR with 0, I get 1, and 1 XOR with 1, I get 0, right? So given that, so I know that C equals to 1, C equals to 1, C equals to 1. These are what I mean, right? Ciphertext equal to 0. So now that I know this information, let's see what is the winning strategy for this attacker. So as you could see, I am generalizing, and I say that for any algorithm A, no matter what algorithm A you design, you can have different value for R, and then once you find R, this one is set, fixed, and when you find S, this one is fixed, right? So no matter what algorithm you come up with, in a nutshell, what would change is this value of R and S. So I just treat them as a parameter, and then that would help me to solve it for any A, no matter what algorithm A is, okay? So when C is 0, I'm using this piece of information over here now. When C is equal to 0, with probability of R, I would say this is 0, the message was 0. With probability 1 minus R, I'm going to output this one was 1. Again, over here, I can do the same computation using the adversary algorithm. So looking into the C equal to 1, with probability S, I will output 0, and probability 1 minus S, I'll output 1. I can do the same computation over here. So C is 1, so S 1 minus S, and this is going to be 0, and this is going to be 1, and then again this one. So C equal to 0, I go back and check this table over here, and I can see that, okay, probability of R and 1 minus R, this is going to be 0 and this is going to be 1, right? So now that is given, so I can see what branches the answer was actually correct. So the message is 0, the ciphertext is 0, and over here it correctly said that the message was 0. Over here it would be this branch, and in this scenario, whenever he says message is 1 is correct, so this branch and this branch. So in half of the scenarios, no matter what algorithm A was, his guess is correct. So that is given. The next thing I want to do is that I want to compute the probability of these branches. I add up the probability of these branches that the adversary was correct, right? So I think I have summarized that computation over here, right, over here. So we say that the probability of adversary to given the CI and he output the correct corresponding M is this 4 scenarios. The first one is that the ciphertext was 0 and he says the answer was M0 and M was actually 0 and it happened when key was 0, and so on and so forth. So basically I'm writing down all this, branches. So probability of message to be 0, the C was also 0, the key was 0, and then that is going to be R, and so on and so forth. So after I substitute this value for every of these branches, we can go back and check that with the computation tree. So I get these answers, and as you could see over here. If we rearrange this formula, you would get to something called R plus S, P minus P1 over 2 plus P1. So I'm going to define a new variable called T, and I'm going to let T equals to R. To just simplify this equation a bit more, I'm going to define it to be R plus S divided by 2, okay? And then the value of T, let's say, what would be the range of T? I know that R is based on this definition of algorithm A. R could be some value from 0 to 1. So maximum is 0, and maximum is 1, minimum is 0, and this one is fixed. And similarly for S. So given that, if maximum R is 1 and S is 1, so this is going to be 2 divided by 2 is going to be less than or equal to 2. And in the worst case that they are both 0, so we're going to have 0, right? 0 and all the way, 0 all the way to 1, okay? So this T value is something that is between 0 and 1. So that means that I can rewrite this equation as P1 plus T times P0 minus P1, okay? So this is, I think, a short form of showing what this formula looks like. And if we assume that, this was the case, so now if I want to show this equation in geometric, I can show that if this is P1 and this is P0, then there is a space in between these two. And depending on what value of, what value for T I choose, then I'm going to land somewhere in between these two lines, right? This winning probability for this algorithm, generic algorithm A that we've computed. But no matter what we do, the best probability that we can achieve, if you really tune R and S well, we can reach to the maximum of either P0 or P1, whichever is the maximum. We would maximize this equation if we tune T very well, so we would get to one of this P0 or P1. So again, one more time, this is something that looks familiar for you guys, right? So no matter what we do, the best probability that we can achieve is less than or equal to this one. So the best thing that he can maximize his probability if and only if he would just stick to the distribution of the message space in the first place. That is the best strategy that the attacker can come up with. And that was a piece of information that was publicly available. So once again, we show that no matter how much computational power the attacker got, no matter how much, what different strategy he choose for, winning this game, we just generalize it with the algorithm with, with parameter R and S. And then the best thing that he achieved is to actually stick to the distribution of the message space, and basically the ciphertext that we provided to the adversary did not help him at all. So that is the biggest thing for the adversary over here. Any questions? So I think the magic that we use here is this computational tree, assuming that we have all possible scenarios that could happen. And we go ahead and check from all those possible scenarios, what scenarios are possible, going back to this computational tree. And then from all those possible scenarios, no matter what algorithm A is, at the end of the day, he's gonna guess with some probability either this given C equal to 0, it was the encryption of M0 or M1 with some probability, and when C equals to 1 with some other distribution, supposing algorithm A is very sophisticated. We've shown that no matter what the distribution of PM is, as long as the key is chosen uniformly random, then no matter what algorithm A would do, then there is nothing better than, he would learn nothing but the distribution of the message space. So which means that he better stop using his computational power and just rely on the distribution of the message itself. And if 0 occurs, for example, 90% of the time, and 1 occurs only 10% of the time, so it means that the adversary can actually win the game 90% of the time if he just outputs 0. No matter what C we give him, he should only output 0. He should only output the message was 0, and that would help him to win 90% of the time. So I know that, again, you guys are saying that the adversary can win, but what happens, we keep encrypting the message 1 or just bit 1, and we transfer that over the line. So based on this algorithm, the adversary always guessing that we are actually sending 0, but actually we are not. We are sending 1. And that is, the way that we can show how we can achieve a perfect secrecy. So I think when we would start to get to see some algorithms that are not perfectly secure, then things would start to make a lot more sense for you. So let's move a little bit away from that concept of perfectly secure and see what are the other chances or choices we have to see any other versions of this unconditionally secure. So we said that one-time pad is actually a very good algorithm. We show that it is perfectly secure, and also we discussed that it is not a practical algorithm. It is not a practical algorithm. The reason for that was because, first of all, we have to have a uniform and random key, and we can reuse the key for every message M or different message that we want to encrypt. We show that we have to use a fresh key. We can't reuse the key, otherwise, we would leak a lot of information. So somebody could think that, is there a way? Okay, now we know that this, original one-time pad algorithm is not practical. Is there a way that we can turn this algorithm into a practical algorithm? So the answer is yes. We would start to discuss a lot of different versions of this, but now we just want to keep it short and see how can we do that. So in here, we would have, again, Alice and Bob that would basically share, instead of a key, they would share a short seed. It's also known as key, but it's a little bit different here. We want to denote it by S. This S is a few amount of bits that happen to have a high entropy, and they both suppose that they have shared this small size of seed S together. And now we are going to use a new algorithm called pseudo random bit generator, that we call it PRG, with input S. And then we are going to, this algorithm would take this short few amount of bits, and he would extend them to a larger amount of bits that we're gonna treat that one as a key for one-time pad. So if I want to show how this PRG works, is suppose we have PRG here, and then we give him 3 bits, 0, 1, 0. Okay, this is a polynomially timed algorithm. It is important for this one to be polynomial time, although if it takes exponential time, then or encryption would become exponential time. And then it will convert this one into many more bits. So maybe over here, so I would turn this one 0, 1, 1, 1, 0, 1, 0, 0, 0, and then 1, 0, 0, right? And you see that we get r bits, if we assume we input r bits, so this algorithm outputs r to the power 4 bits, right? He would just, we would have a lot more bits than what we have made before. So over here, what we have, for example, as input, we have truly random bit. And then what we get over here, we get pseudo-random bit. How so? We said that the PRG is sort of a polynomial time algorithm, which means that, for example, this algorithm would take the first 2 bits and do some computation to compute the 3rd bit, right? And then it's going to take these 2 bits and do some computation to get this bit, and then this 2 to compute this bit, and then basically this 2 to compute this one, and so on and so forth. So the input is provided by us. It is assumed to be very truly random, and then he would use that truly random bits to generate something that we call it pseudo-random bits. But I know it sounds a bit odd. The first question is that what do we lose to get from truly random bits to pseudo-random bits? So that would be a very interesting question to answer. To answer that question, I want to design a very, simple PRG, and then we can discuss together and see how is it so. So suppose that in my imaginary pseudo-random number generator, I receive a seed of 2 bits, so S0, S1, and S2. So, I just get two bits. And then I would give this one to my PRG. And then my PRG is, we said that it has to be polynomial. And it cannot, PRG itself cannot, access to any other source of randomness than the S that we provided to him. Otherwise, we cannot reproduce the same result with the S. We need that to happen. So since this is polynomial and the only random bits that it has access to is this S, so I define it to be like this. So I basically try to extend the bits by 1. So I would just, this is going to be S1, S2, and then S1 XOR by S2, right? So this is I'm not arguing this is the best design, but at least this passed the definitions, and I'm just keep consuming the same thing. So I extended with 1 more bit. That's all it does. So let's see the computation tree now. So the truth table. So we have S1, and then I have my PRG. So with given S, I want to see what outputs I can produce. So all the possible values that I can have is 0, 1, 1, 0, and 1, 1, right? And then looking into this definition, I can see that my PRG, depending on this computation, is going to extend. So the first 2 bits are being copied exactly the same, and I'm just extending 1 bit. So 0 XOR with 0 is just 0. For the second one, I have 0, 1. 0 and 1, XOR them together is 1. 1, 0, and then XOR them together, I get 1. And then 1, 1, and XOR them together, I get 0, right? I managed to extend from 2 bits to 3 bits, right? And these are all the possible values that I can generate based on, this PRG that I have defined. But I want you to now invite you to look at the true random number generator. If we had a true random number generator that we ask him to generate 3 bits for us, I'm sorry. Let's look at what are the possible values we could generate with this true random number generator. So we can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 100, 101, 110, and 111, right? This is a true random number generator, and we ask it to just generate 3 bits for us. And these are all the possible values that it produced for us. And can you see the difference and comparing to the PRG now? Any opinion? Looking into this too, the very first observation that we can have is that we are missing. So we made 8 different possible values we can make with 3 bits. But with this pseudo-random number generator that we have, well, the point is you can replace this one with some other stuff, but no matter what, you can use only 2 bits. So it would be challenging, extremely challenging to produce all these possible values based on these 2 bits that we have there. So why pseudo-random number generator and it is not true random number generator? Because you see that we miss half of the values that we could actually have with 3 bits. And a pseudo-random number generator in reality would also look like the same. We cannot get to the true random number generator because if you see, the range is cut into half. So we are trying to get close as much as possible to a true random number generator, but unfortunately with the designs, there is no way to catch up with the true random number generator. So if somebody just give you 1 or 2 bits of random, and then the best case that we can generate up to now is to just convert them into, cover half of the all possible 3 bits that a true random number generator can make. So that's why we call it a pseudo-random generator. We can never achieve true random generator for now. That is what we've learned for many years. So, okay, given that, so now we accept that we cannot produce true random bits, but, well, we can at least do our best and try to get as close possible to the true random number generator. So somebody might ask that, okay, so suppose we have the true random number generator, how does that help our algorithm over here? So now we have algorithm A, Alice, and we have Bob. Let me write their names so that we don't get them confused with attacker. So they share this 3 bits before, so 0, 1, 0, right? And then Alice would compute the key to be pseudo random generator of S, and that algorithm would output some bits, let's say 0, 1, 1, I don't know, 0, 0, 0, 1, 0, 1, 1, 0. And Bob would do the same thing and compute the key to be PRG. Given the same seed, you would get the same output, right? And now Alice can send messages to Bob by the way of MAI XOR with KI, right? And every piece of bit of message would get encrypted with 1 bit of message and sent over to Bob. And now, thanks to this algorithm, we can expand the keys. And Alice and Bob, with the short amount of key that they have shared before with each other, they can start to encrypt and send the messages back and forth to each other. So going back and see if this one is why this is computational version and why it is not perfectly secure, it lies in the fact that we replace the true random key, uniform key from all possible values with just like we basically cut the space. So we know that half of a space for the keys are not possible. So if you go ahead and do it for homework for yourself and draw that computational tree one more time, then you would see that actually plotting and doing some computation would give advantage to the adversary because not all the possible keys would happen to show up, and therefore that would really affect the ciphertexts that we would generate. And it is possible for some messages to only, map to one unique ciphertext, and that would help the algorithm or the adversary to give a better guess for some conditions at least. And even for some condition, he can give a better answer or guess correctly that already violate the, or rule that the adversary would never learn anything beyond the distribution of the message space. But clearly, we see that when the key space is smaller, the computation would actually does help the attacker, and the attacker can, utilize that computational tree to give a better guess, and therefore the probability that this algorithm A is correct is gonna be way higher than the distribution of the message itself. So I hope this really give you an abstract. A lot of time you see on some libraries that they are providing you pseudo-random bit generator, and you always wonder why the heck do they call them pseudo-random number generator? Why not just like random number generator, or why not true random number generator? So I hope that this simple design over here really help you to understand that no matter how hard we try, we cannot get any close to the range of those true random number generators. And obviously missing half of the space, as this just 3 bits. And if I go higher, you will see that this the distance would get larger and larger. And therefore, the difference between the pseudo-random number generator and the true random number generator become more and more significant. And just because of this flaw or inability to generate a true random number key generator, then unfortunately any practical version of on-time pad would turn into fail. We fail to prove it to be perfectly secure, so it is going to be computationally secure. As long as it is going to be secure, as long as we assume our adversary is basically computationally limited, or we call it computational version. So I hope that this example really draw the line between these two versions, and hope you to understand, and at least we've practiced one algorithm that is not perfectly secure.
Can I?
Yeah, go ahead.
I have a question, sorry. What we're doing right now is still a one pad, which means that we would still send one different S per message we want to send. And this gives us the advantage that the S that we're going to send is shorter, and that we can adapt it to the size of the message. Or why are we taking on pseudo randomness if we're already generating true randomness with the S?
Right. If you consider this computational tree, right? So the keys that are coming into our system, the sequence of these keys that we are ready to go. The sequence of this key that we are generating is going to depend on the previous ones, right? So for example, this key is going to depend on these two, and so on and so forth, right? So if you see this one see this picture for n-bit message, and you want to encrypt that n-bit message, then you will see that unfortunately we can generate all the possible key from the key space. And when you cut the key space, then unfortunately we would move from that true random number generator, from that unconditionally secure one-time pad to its computational version. The one other reason that you can imagine is that, well, since we get to cut the keys into half, then the adversary only have to guess half of the keys, keys from the all possible keys to run a brute force, right? Suppose that you start to encrypt n number of bits. So if you want to generate a true random key from n bits, then you have to write down, 2 to the power n different keys. And suppose that the adversary wants to do a brute force, and therefore we know that the 2 to the n is a huge number. So suppose you try to decrypt all those messages with all these different bits, 2 to the n different bits, and that for loop would take forever, right? But now, because the imperfection in our key generator, we have a lot less keys to try, and that would really cut the computation, that for loop, to something way more smaller. And that's why we would walk away from that perfectly secure to just computationally secure.
Yeah, that I understand. But what I don't understand is, why are we even, like, if we can generate a true random S, why would we bother generating a pseudo random?
Oh, okay.
I don't know.
I got your question. So normally, computing a very large stream of keys with a very high entropy would be very costly, or it is impossible with computers to generate. So what we often would do, we accept a small key from a small source, and then we would use algorithms to expand that. For example, if you want to encrypt a gigabyte of file, so we need a gigabyte of key, right? With this algorithm, that is impossible to transfer a gigabyte of key. And I mean, not impossible, but it's impractical. So what would make sense is that we, Alice and Bob share a much smaller key, maybe, for example, 100 bits. And then we feed that same 100 bits to an algorithm that, it's a very well-designed algorithm. And then that algorithm expand that 100 bits to like a gigabyte of worth of bits. And then we would use that one to encrypt the message. So this is where the pseudo-random number generators come into the game. So we often have access to a few randomness bits, and we always want to expand them because we need more, longer number of bits. And the only way that we can do that for now is to use something called pseudo-random number generator.
Thank you, I understand.
Mm-hmm. So if I want to give you a very good answer, I mean, how can a computer generate a true random bit? What are the random sources that you have in your computer? The pattern that the user type, I mean, the time that it takes to a key to be pressed, or the entropy of the characters that he types, if it is English text that he's typing. So it would be very different than if he just type random nonsense string, because we have patterns in English words. If you want to see the utilization of the disk, that is not truly random. It has been shown that it has pattern. If you want to use the network traffic to generate the random bits, so we know that the network traffic is mostly TCP/IP or whatever different algorithm. They come with a fixed header, so a lot of information there is repeated. So that is also not a good choice. Power consumption of the computer along, again, that can have repetition, so it cannot be a good source of randomness. In a physical world, we too can just flip coins, if we say that the coin is fair, and then we can easily generate bits that are, like, for example, the second time that I flip a coin, the result would be independent from the first flip, and so on and so forth. But in computer, it would be extremely hard to achieve this, because if you start to read your hard disk drive, the next, let's say every 1 second you get a snapshot. When you start to read a large file, then for some good amount of time, you'll keep reading from the disk. So the power utilization of the disk would remain high for some time. So there is there is no independency between those bits that we would generate, because the power consumption would remain high for some good amount of time for that file to be read, or many different scenarios. So that is why it is hard to generate this long S from the very scratch in the computers. This is very challenging. So the only way that we can basically achieve this is that we expect that somebody can give us as an input a small or a few bits that are independent from each other and they are totally random, and we use that one as a source. That seed also would sound like a source, and we try to expand from what we have, and that's why we use pseudo-random number generators. All right. If not, I think we are missing break times. I'm sorry for those that want to stick to the exact time. Sometimes it would be challenging. So I think we would come back at 10:10, okay? We just miss the break time, so it doesn't matter.